Now we're going to look at how we can calculate confidence intervals for proportions using the central limit theorem. So suppose you randomly took a poll, asked 400 students some yes or no question. I just made this one up, whether or not they were in favor of moving the academic calendar to start a week earlier. And they have to tell you either yes or no. Suppose 192 students were in favor and the rest were opposed. Okay, well, based just on your sample, you don't have over 50% of the vote in favor of this change, at least based on the sample proportion. But a reasonable question is to ask, what can we infer about the population proportion just from this sample? And this is where a confidence interval is very useful, because we'd like to add some error bars to that 192 out of 400 sample proportion to see if truly we can conclude, less than half people in the population are in favor. So to do this, we're actually going to reframe how you may have been thinking about proportions. Well, let's just do it with a simpler data set to start. So suppose I just have 10 entries of zeros and ones. And again, in a yes or no poll, you could think of 0 as no and yes as ones. Notice if I just sum the data, well, that's actually going to give me the number of yeses. And so if I take the average of the data, that's actually going to give me the proportion of yeses. So it turns out that if your population consists of ones and zeros, we've called that in the past, that's a Bernoulli distribution, then the average of your sample from that type of distribution is actually the same as a proportion of ones in the population. And same thing, the sample, So if your population consists of ones and zeros, which we've called Bernoulli distributions, then the population average is the same as the proportion of ones in the population. And the same will hold for sample averages in terms of them being the proportion of ones in the sample. So let's use this to our advantage, because we know the central limit theorem works when we're working with averages. And so instead of having a population average here at the center of this normal distribution, we'll have a population proportion, because that can be thought of in terms of an average. And then I have, this is one standard error for this proportion statistic. And if I want, for example, the 95% confidence interval, well, then I'm going to look at my sample proportion, and then I'm going to add and subtract 2 standard errors to this sample proportion to get my 95% confidence interval. So it's exactly what we've already learned. It's just realizing we can reframe a proportion as really a mean. So at the end of the day, the confidence interval, 95% confidence interval for my population proportion will be the sample proportion plus or minus 2. Again, that's for the 95 part, times the standard error of the sample proportion. So I know my sample size in this. This was 400 students. Now the question is, wait a minute, I need to know what's the standard deviation of a 0-1 population. Well, we've seen this before, because like I mentioned, the 0-1 population is akin to just a Bernoulli random variable. So suppose the probability in the population of a value of 1 is lowercase p, then the probability of 0 is 1 minus p. And we can actually derive the standard deviation for this. And we've done it before. So as a reminder, here's my expected value. On average, I will get a value of p across many samples. And then my variance is p times 1 minus p. Again, from when we did before, the expected value of x squared is p, and then I'm subtracting the square of the expected value. If I were to plot p times 1 minus p for p values between 0 and 1, because again, it's a probability, I get this shaped curve. And then if I take the square root, which is the standard deviation, I'm getting this shape. We'll come back to this shape. It's going to play a role in our next video. For now, the key takeaway is the standard deviation of a Bernoulli distribution is the square root of your probability of a 1 times your probability of a 0. All right, so let's use this now in our original problem. So I want my confidence interval. I don't know the standard deviation for the population because I don't know the probability of a 1 in the population. Right? That would be great if I knew that, because then I'd be done. How many people in the population are in favor of this? So P is unknown, but I know that the standard deviation is the square root of P times 1 minus P. Just like we did in the previous video, we can estimate this value of P here, using the actual sample data. Okay, so it's not perfect, but it's an estimate. And that, in this case, from my sample, P is approximately equal to, well, the number in favor, so 192 over 400 based on the sample, from my sample. So that's what I'm going to use here. I'm going to take my sample proportion, so my confidence interval, and this is a 95% confidence interval, is taking my sample proportion, which is 192 out of 400, plus or minus 2 times square root of P times 1 minus P over the square root of 400. And again, I'm approximating P with the sample proportion. So I'm going to do 192 out of 400 plus or minus 2 times the square root of 192 400 times 1 minus 192 out of 400 all over square root of 400. And that's going to get me 192 out of 400 is going to give me 0.48, so 48% in favor, plus 2 times, and this is just going to be approximate. This ends up being 0.02498. It keeps going, but that's pretty good. Implies, here's my interval. So when I subtract that and add it, I'm getting 0.43 approximately as my lower bound and 0.52996, so basically 0.53 as my upper bound. And this is my 95% confidence interval for the population proportion that's in favor of this change. So this provides a lot more information than just my sample proportion, because now I realize, well, this confidence interval includes 50%, includes values even greater than 50%. So it's unclear to me that just using this sample data alone, it's not clear to me whether or not the majority of people are really in favor of this change or they're really not. These error bars are too wide, they overlap 50%, so it could go either way. The true population proportion may very well be more than half, or it may very well be less than half. If I needed a more satisfactory answer or something more specific, I could always go poll more than 400, because that will at least decrease my interval by increasing that denominator there. And that may help me get a narrower interval at least. So this is an example, and using this, the population proportion as a proxy here when calculating the standard deviation is fine. It is one choice. The other thing that you can do to be extra safe, because it's quite possible that this is incorrect, is actually to go back and look, let me come here, at the plot of this. And you could just do a worst case scenario if you want, by saying, well, worst case scenario, the biggest the standard deviation is ever going to be is 0.5, because the worst case happens when your probabilities of ones is equal to your probability of zeros, and you get a standard deviation of 0.5. So if you wanted to be even safer in making your confidence interval, you could actually put that here as your standard deviation, like worst case, and I could just replace this term in the numerator with 0.5. That would give me an even wider confidence interval, so it would be less informative, but it may be a little safer in terms of not having to make this approximation. In the next video, we're going to look at this idea of how we can determine sample size and what sample size we may need to get a level of accuracy to our satisfaction. So we'll look at how you design experiments using properties of the central limit theorem and proportions.